hear us.
Right.
Over there in Zoom land.
Okay, so we're gonna start our next talk very soon. Okay, our next speaker is Tyler Meadows from Queen's University. He's going to talk about self-cycling fermentation with multiple nutrients.
Okay, thank you. I also want to thank the organizers for the invitation. For those of you who don't know me, I was Gail's most recent PhD student. I graduated about 3 years ago now. And since this is a conference in honor of Gail's birthday, I figured it would be fitting to talk about my PhD thesis, which I did under the supervision of Gail. So what we were doing was looking at the nutrient-driven self-cycling fermentation process with multiple limiting nutrients. So sort of an outline of the talk, we're going to first focus on what exactly self-cycling fermentation is, and then I'll go through what the results are known for the single nutrient case, and then we'll complicate things by adding multiple limiting nutrients, and modeling changes a little bit at that point, and some of the results also get a little bit extra complicated. So self-cycling fermentation is a bioengineering process that's used for cultivating microorganisms. It's used in the production of biofuels, in wastewater treatment, in the production of things like ethanol. Recently, it's been shown to be effective for producing shikimic acid, which is one of the active ingredients in making Tamiflu. And it's an alternative to continuous culture reactors. So if you think chemostat, which Gail's really well known for studying, these are continuous reactors where you have a continuous inflow and a continuous outflow. Self-cycling fermentation is a sequential batch process. So we're looking at periodically draining and refilling a tank. So the benefits of this include that potentially we get some sort of increase in production if we're looking at culturing microorganisms, or if we want to harvest some of this byproducts, we can expect more over time of those things. And if we're thinking about this in terms of a wastewater treatment process, then we'll potentially gain a little bit more control in what we're releasing back into the environment afterwards. So sort of the idea behind this process in terms of increased production is, if we look at this bacterial growth curve over here, bacterial growth usually goes through 4 phases. We have a lag phase where once we've added some nutrients, the bacteria are slowly figuring out that food's there and tuning their metabolic system so that they can uptake and use these nutrients. There's an exponential growth phase where bacteria are growing very quickly. And then there's a stationary phase where they've just about used up most of the nutrients and are reaching a quiescent phase. And then there's a death phase afterwards where the number of bacteria is decreasing. So the idea behind self-cycling fermentation is to keep everything in the exponential growth phase as long as possible, so that you're continually producing more and more bacteria at a high rate. So this works, it's a computer-driven process, so it works by taking a tank, filling it with nutrients dissolved in some solution, and you inoculate it with some microorganism, typically yeast or E. coli, that you've genetically altered to produce whatever you want to produce. Or in terms of wastewater treatment, you have some sort of bacteria that, say, degrades nitrates and into some less harmful form. These microbes feast until they've reached some decanting criterion, and this decanting condition could be anything from, say, concentration of some produced compound, concentration of the input nutrients, or just a certain amount of elapsed time. At that point, the computer tells the tank to drain. It goes through a decanting process. It drains partially and then is refilled with a fresh solution of nutrients, and then the whole process starts all over again. So why bother modeling this? So there's no guarantee that we're going to reach the decanting period even once, let alone a lot of times, which is what we're going to characterize success of the reactor by. So for this to be successful, we need this to repeat just with the computer triggering the decanting phase and not having a human have to intervene and re-inoculate the tank with more bacteria. On the other side of that, the whole point is to increase production or consumption of something over what we would get with a continuous reactor, and modeling gives us a framework to figure out whether or not that's something we're actually doing. So the point of the talk today is going to be sort of focusing on this first reason to model here, in that we're going to look at different conditions to ensure successful operation of the reactor under different scenarios. So this all started as a part of Stacy's PhD thesis in 2001, okay. A little bit late with that. So Stacy was looking at the single nutrient, single species case with this. She also did some extra work with competing species and an age-structured model. But I'm going to focus on just the first bit, which was the single species, single nutrient growth. So this model is set up as an impulsive differential, or a system of impulsive differential equations. We have a reaction phase in which bacteria are consuming a nutrient at a rate given by f of s. So this is our uptake function. And the growth is dependent on the uptake of this nutrient, and then they decay at some decay rate. The decanting criterion is given when our nutrient reaches a fixed threshold given by this S bar. In the decanting phase, we drain out and refill part of the tank. So the limiting nutrient is drained out, and what's left is 1 minus R. So R is the fraction that we're going to have left, or fraction that we drain out at each step. So what's left is 1 minus R times the concentration before an impulse, and then we add in R times whatever the concentration of our input nutrient is. And then the bacteria, what's left after an impulse is just 1 minus R times what was there before an impulse. Stacy looked at specifically the monotone increasing uptake functions. So these are functions that are 0 at 0, always positive, and increasing as S gets larger. So in this case, here's sort of an example trajectory here. We have our bacterial species is increasing. Here our S bar, our decanting criterion, is set at 0.1, right? So we can see that the nutrient has dropped to 0.1 here. Our decanting happens, and we end up with slightly less bacteria, and this process kind of repeats, and we can see that it eventually reaches a periodic solution in which this is just sort of happening over a fixed period. So this would be considered successful operation of the reactor. It's possible that we've set this up in a way that there's no periodic orbit, and this doesn't happen, in which case X, our population of bacteria, just decays to 0 as time goes to infinity. So it turns out it's not very useful to look at these trajectories, and it's much easier to look at everything in phase plane, as is typically the case. So here's sort of an example of something that could happen in the phase plane. We have an initial concentration starting over here with initial concentration of S at 1 and initial biomass at about 1.3. Our growth happens, the amount of nutrients in the tank decreases while the amount of bacteria in the tank increases. If we don't allow for impulses and we just follow the ODE system, eventually everything will decay to zero. But once we reach our decanting criterion, we're mapped to somewhere over here. And this ends up being a convex combination of this point with this point, which is our initial or our input concentration of S, and no bacteria. So we can follow this along here. This is where we get mapped to, and then the process repeats, and then we would get mapped somewhere else, and this kind of repeats on and on and on. Okay. So we can see here that there's going to be a periodic orbit, and this is going to be the curve that has endpoints that lie both on this line of slope, or this, sorry, line segment connecting this point with our input concentration at zero. Okay, so they're able to go through and show analytically that you're going to have a periodic orbit only if the growth along this trajectory here, so this red line, is positive. So essentially we need this endpoint to be higher than this endpoint, and that's characterized by this integral here. So if this integral is positive, then there is a periodic orbit. Unfortunately, that's not enough to guarantee that you're going to converge to the periodic orbit, but it ends up being a minor result in this case to show that as long as you end up with one impulse, at some point you will eventually converge to this periodic orbit. So the case where you're not going to have an impulse is, say, if we go back here and you start somewhere over here, and maybe there's a slight decrease to zero before you actually reach this impulse condition. So that's the one case where you wouldn't actually converge. Okay, so single species, single nutrient growth, but in this case, considering a unimodal growth function, this was a result of Guihong Fan, one of Gail's other PhD students, but this was her master's project that she did. So looking at an extension of what Stacy did as part of her PhD thesis. And in this case, we have a unimodal growth function. So this is the idea that the nutrient concentrations become inhibitory at high concentrations. In this case, they weren't as relevant in the single nutrient case, but when we're considering chemostat models, we'll often talk about break-even concentrations. And with these unimodal growth functions, we're going to have two. We'll have a lower break-even concentration where the function is equal to the dilution rate, or in this case, break-even being growth function is equal to the death rate, and a larger one, sigma. Otherwise, this is the same model. All that's really changed is just our uptake function f. So things get a little bit more complicated here. So we see in this, we have successful operation with some initial conditions, and I've taken the same model and taken different initial conditions, and we have what looks like a single impulse and then failure. So our bacterial population has decayed to zero over time. And this is something that can happen as a result of an initial dip in the bacterial concentration. So we'll see that this yellow curve corresponds to this bottom picture here. So we have initial increase, and then our state is mapped somewhere over here where it needs to decrease to start off, and our population will approach zero. And we can see actually, it's maybe clear, it's maybe not clear, but each of these curves are identical. They're just shifted vertically in this picture. So if we take one of these curves and move it too low, it needs to intersect the s-axis before increasing again. So this all can be formulated in terms of these break-even concentrations and more integrals. So if our function is unimodal, our impulsive system will have a unique periodic orbit as long as this inequality holds. And this inequality really is just saying that the growth either needs to be completely positive, or it needs to be at least bigger than the minimum, the loss that would be, what am I doing here? So sorry, let's go back here. Where this ends up here, this integral term in the next page is just showing the difference between here and the minimum. So this minimum needs to be shifted high enough so that it doesn't intersect with the s-axis. Sorry, that's all that's saying. Either it's completely positive the whole time, or at least it doesn't dip too far. And then there's also convergence results where it says if you get 2 impulses at this point, then you're guaranteed success. So as we had in a picture back here, it's possible to have 1 impulse and then failure, where in this case, as long as you have 2, you're guaranteed to converge to this periodic solution, which is what we would consider success. So where my work comes in is with multiple nutrients, and modeling with multiple nutrients gets a little bit difficult. So we've changed a few things in the model here. So S is now a vector, so it's an element of Rm. We have an arbitrary number of nutrients. We did one project where we only considered 2, and we did another project where we considered an arbitrary number of them. Y is a vector of yield concentrations, or 1 divided by the yield concentrations in this case, and X is still a scalar. We'll notice that we have our decanting criterion has changed a little bit. It's not just equal to some S bar necessarily, because this is a vector. So this is going to be some subset of phase space, just depending on our nutrients. In this case, what I did for my PhD thesis was I considered weakly monotone response functions, or this would be the case where we're considering, I hate when I lose words. Come back to it. So weakly monotone. So these are going to be nutrients that are not replaceable by each other. So they're all essential. That's the word I was looking for. So essential nutrients. So these are going to be things that you need some amount of both of them. And this is characterized by needing that f of s is equal to 0 if any of our component one of these vectors is 0. So there's no growth if you're missing, say, you don't have carbon, or if you don't have phosphorus, you can't grow. You need both in some quantity. What we have pictured down here is one example of this. So also just considering that our function needs to be Lipschitz continuous, because I want to allow for things like a Liebig's minimum function, which really captures the, I need certain things in certain amounts, and yield growth is limited by whatever is the least present one there that you have. Okay, and the monotone part is that if our concentration is greater than some other concentration u, then our function is going to be greater than or equal to this. And I mean greater than or equal to in the monotone dynamical system sense, where the difference is going to be in the positive cone. Okay, so talk a little bit about the decanting criteria. So we talked about we studied 2 different situations. As I mentioned, one we did where we were only considering 2 nutrients. And in this, we were considering that the concentrations of both nutrients needed to be below some threshold. So we had some S1 bar and S2 bar. And this was a paper we did with Tinghao Xu, who was a postdoc with Gail at the time, me, Lin Wang, who's somewhere over there, and Gail. And I'm not really going to talk about this one too much. The details get a little bit messy, especially when you start dealing with this corner, ends up being kind of tricky. In a sort of extension of this, what we started looking at was sort of the case where S2 bar went to infinity. So we're really considering the case where just only S1 bar is important. We realized we could extend this to an arbitrary number of nutrients, so that's what we did. And this ended up being published in 2020. So we're really looking at just the case where one nutrient must reach a threshold, and the other nutrients are just sort of free to do whatever they want. Yeah. So it's the decanting criterion. So we're not limiting, this is not so this is just what triggers the emptying refilling process, right? So S2 is still limiting. It's just, we're not really considering it for whether or not we empty and refill the tank. Okay, so we have an example here. I've taken 3 functions. I'm taking the minimum of 3 Minot growth forms. Why is there some things? Our S1 bar, so this is our decanting criterion. Again, we're only considering the case where there's one of them, is going to be 0.25. And I'm going to drain a third of the tank and refill that with fresh nutrients. That capital D should be a lowercase d. So that's going to be the death rate of our microorganism. And our input concentration, we're going to put 0.5, 1, and 0.5 of the respective nutrients in each time. So for different initial conditions here, we can see that we have 3 impulses and then failure. All right, so this is wildly different from the other case where if we had 2, we were guaranteed success. Something else is going on in this case where we're possibly something different can happen. On the other hand, if I have 0.32, so a slightly higher initial condition of my bacteria, we have convergence to a periodic solution. All right, so analysis of this, the way we went about it was we noticed that if you took the S equations, they all had essentially the same form. They differed in these yield coefficients. So we were able to divide one of the equations by another equation to see that if we projected things onto the S1, Si, or any combination of S planes, we had lines, which lines are nice and easy. This is something we can analyze fairly easy. And then our concentrations here, again, we're still going to notice that this is a convex combination of our input concentration and the point that our concentrations meet our decanting criterion. So if we start with an initial condition here, this will decrease both of our concentrations until it reaches gamma, and then it'll be mapped somewhere over here to a set which I'm going to call gamma plus, and this is just the image of this set gamma under the decanting map. Right, and then things decrease again, and potentially, as long as our bacterial concentrations are high enough, we hope we're going to converge to some periodic solution, which means that our line of our solutions will have the same slope as the convex combination connecting our point at the end here to our input concentration. So this is exactly what we did with this lemma. We define these Lyapunov type functions, VI. So for each concentration, except for our focus nutrient, which is the one that we had our threshold for, define one of these, and we can show that these concentrations are constant as long as we're undergoing continuous dynamics, and there's a contraction by 1 minus r when we have these impulse dynamics. And this VI really can be thought of as a distance between whatever line we have here and the line that has the same slope going through our input concentration. Okay. So as a result of this, if we have an infinite number of impulses, we can see that since we're undergoing this contraction, remember r is between 0 and 1, our lines here will be getting closer and closer to this line through our Sin. Okay, so we also use these to define 2 regions in our nutrient space. So we define first the line that goes through 0 here with the same slope by these VI bars. And we use these to define omega 1, which is the set of concentrations that lie above these lines, and omega naught, which is the set of concentrations that lie below. And we get some immediate results from this as well. One of them being that if our initial condition starts in omega naught, so our line below here, since our lines projected, or our solutions projected into nutrient space here are just lines, they would have to intersect S1 axis before intersecting gamma, so we can't possibly have any impulses, and our concentration of bacteria will go to 0 as t goes to infinity without having any cycles. On the other hand, if our input concentration is down here, we'll get a similar result saying that even if we start with an initial condition in omega 1, where we potentially hope to have success, after a finite number of impulses, we'll end up in omega naught, and then we'll again have x of t go to 0 as t goes to infinity. All right, so neither of these situations are allowing for success. As a result, it's going to be necessary for a periodic orbit for our initial concentrations to lie in omega 1. And as a result of that, we're able to get an existence theorem that's very similar to the other existence theorems. If this integral here, which is the net growth along one of these curves that would correspond to a periodic solution, is positive, then the impulsive system is going to have a unique periodic orbit, and all that's left to do is talk about convergence. And that ends up being sort of a thorny subject in this also. So for convergence, we're going to define first what ends up being the net growth between an initial condition. So if we have, say, an initial condition down here, and then go to the impulsive set gamma here, this I is just the net growth of x along that curve. Pi we define to be the projection along the same line from an initial condition into gamma plus or gamma, and then g, if we have something that's in gamma, is the projection along the convex combination between our point on gamma and our input concentration into gamma plus. Okay. Using these two things, we define two sets. We define G plus to be the subset of gamma plus, so this image of gamma under the impulse map, where the growth from any point along here is positive, and G to just be the projection of G plus onto gamma. So we take the image of this along one of these lines and end up down here. This is G. And ideally, what we want is for an impulse to end up into G plus, and that should be something that guarantees us success from then on, because we know growth from there will be positive. That means we have a very good, well, we're guaranteed to be able to grow until we reach our impulse condition again, and then we'll be back here and be able to repeat the cycle. Unfortunately, we can't find explicitly what a formulation for G plus. So we need to do an approximation with this, and what we can do is define a ball around the periodic solution that lies within G plus. So we have some rho greater than 0, so that this ball is a subset of G plus, where remember we had these VIs were scalar functions, so we take the absolute value of those, and that gives us a measure of distance between our periodic solution and whatever point we have. Okay, so I guess before defining our ball, if we have some input concentration in our good set and our growth from along the potential periodic solution is positive, and we take something that's going to be in this ball of radius rho around that, remember this is going to be something that's in our growth set. As long as our initial concentration of biomass are large enough, then we're guaranteed to be able to reach the impulse set once. And then from there, we'll be mapped to our omega plus, where we're guaranteed to be able to grow until we reach the impulse set again and again, and eventually converge to the periodic orbit. If our initial concentrations are too low, then our bacteria will die off before we get a single impulse, and then we won't have success. Additional result with this is we're able to define the minimum number of impulses, so that's this n rho, sorry, just by rearranging the contraction of our VIs. And yeah, so we're defining the minimum number of impulses that are required to be able to enter this ball of radius rho around our potential periodic solution, and define X, this capital X here, which is the minimum amount of biomass that we need to be able to guarantee that we'll be able to get through all of those impulses before we reach the impulse set. So we can see this is sort of sum of a bunch of contractions with our growth at our image of the impulse map composed with our projection onto gamma a bunch of times. So it's a little bit complicated, but this is the sort of thing that you can plug into a computer and it will actually spit out all of the calculations. So if we go back to the example that we had before, so nothing's really changed here, we're able to calculate that our n row is 6. So we require 6 impulses before we're guaranteed success. There are some initial conditions where if we have 5 impulses, we would fail. And we can see here there's an example where we have 3 impulses and then failure. And our minimum amount of biomass that we require is about 2.98. We can see this 2.8 is somewhat less than that. While the 0.32 is something larger. Okay. So what we've learned from all of this. Convergence to a periodic solution is very initial condition dependent, but you can calculate all of the conditions that you need beforehand, so you can determine whether or not you're going to be successful before you even start up the reactor, which is important. Unlike the single nutrient case, failure is possible after a large number of initial conditions, but we do have an upper bound on the amount of impulses that you'll need from any initial point to be able to figure that out. And given that the reactor is calibrated to have a periodic orbit, if you start with enough biomass, you're basically guaranteed success. So I guess the moral of the story is inoculate with a lot more than you need, than you think you need. So other directions that that I am looking at with this is more general decanting criteria. So we had those 2 different decanting criteria we set, where one was essentially just a line or a hyperplane separating phase space into 2 sections. And another one was this sort of box separating the origin away from the rest of phase space. So what I'm looking at is some convex set around the origin as a decanting criterion and seeing if I can get anywhere with the analysis with that. Also looking at multiple nutrients with unimodal responses. So unimodal responses get a little bit more complicated when you're thinking about things with multiple nutrients, and you have to adjust a little bit with that. I'm happy to talk more if anybody has questions. And also a single nutrient, but the decanting criterion depends on produced compound. And that ends up being important because that's one avenue that people are looking at to scale these reactors up to production scale, is monitoring the production of certain secondary metabolites. All right. And I think that's it for me.
Okay, any questions from the audience?
So alternative question is to, again, maximize the